Continuing the last time, let me give another example of two-dimensional dynamical system, which is a simple model that represents the population of two species, one predator, the other prey. For example, this is the population graph for two animals, lepus and lynx. Which one is predator? Lynx eat snowshoe hares. It's about hare and lynx. And you can see the oscillating behavior over time. And the simple governing equation is as follows. Let x of t be the population of rabbits and y of t the population of the predator, say lynx. Lynx look like this. We write the increasing rate of the rabbit population is proportional to the population of the rabbit, possibly without the presence of the lynx. It's natural to assume that the increasing rate of the population is proportional to the population itself, as usually population grows geometrically. But if there's a predator, then the increase of the increasing rate can be smaller. And if the predator is more than certain threshold, then actually the population can decrease. So let's call the threshold to be b. Then you get the following additional factor, b minus y. So if y, the population of lynx, is bigger than the threshold b, then the actually start decreasing. Similarly, the population of the predator will increase with its own population without the rabbit. The predator needs rabbits. So if there are less rabbits, then the increasing rate will be smaller. And if there's a too small number of rabbits, so if it is less than certain threshold, then actually the population of lynx can decrease. So actually I have to use a different y, and there must be some threshold d such that if the rabbit's population is less than d, then the growth rate can be negative. So this simple model have 4 coefficients, and we have 2 variables, x and y, and actually they're time variables. So we can rescale the 3 variable time, x and y, to remove 3 out of 4 variable. After rescaling, we can obtain a system with just single coefficient instead of 4, and with the same structure of the equation. We can obtain the first integral of this system, dividing the second equation by the first, and then collecting the same variable into same side. I just found a mistake. This is not dt, but dx. Now each side you can integrate, and I put the integration constant c, which can act as the first integral of the system. The right hand side is independent of time t. Going back to the original equation in the pink box, we can find out what's the steady state. Steady state is where the dynamical system stays at the same point. It's where x dot and y dot becomes 0. If you look at the right hand side, that happens exactly when x equals 0, or x equals 0 and y equals 0, or x equals 1 and y equals 1. Of course, x equals 0 and y equals 0, that's just no population, so that's extinct state. Remember, when we first derived the equation, we put b as the threshold of the population of the rabbit, d as the threshold, population of the predator, and d as the threshold population of the rabbit. So depending on whether it goes above or below, the population of the other decrease or increase. and the threshold after rescaling becomes exactly 1. So 1 comma 1 is both population is exactly at the threshold. That's where both population coexist without changing. And if you calculate the value of c at that point, it gives minus 1 minus mu. If you draw the contour lines for the same first integral c, then you can see this kind of picture where this point at 1 comma 1 that I draw a blue dots, that's for the coexistence state. And then you have bunch of closed orbits around that point which move in this direction. That's counterclockwise direction. So x-axis was the population of the rabbit, y-axis was the population of the predator. So you can see that first x-axis, the population of the prey grows, then it follows that the population of predator growing, and then it follows that the population of the prey as a result decrease, and then it follows the population of the predator also decrease. So this kind of periodic behavior showing up. And such periodic behavior is what we've seen in the Wikipedia about this oscillating population behavior of these two species.